Welcome to this 18th class in this physics of materials course. In the last class we looked at the Fermi-Dirac statistics and we started deriving the expression for the Fermi-Dirac statistical distribution. So we progressed to some extent, we will continue from there today and complete this derivation and try to understand what this derivation implies. Okay. So this is what we will do. So I just put down in words what we have done. I put down in words the major expression that we arrived at, from where we are actually going to narrow down to the solution that we are looking for. Okay, so this is the expression that we got. In words, it comes to something like this. Probability of occupancy of a state probability of occupancy of a state at energy level E1 is equal to we will just say sum. So sum over all possible distributions of probability of occupancy of a state at energy level E1 when the distribution is a certain distribution that we are calling as n bar into alright. So this is the general expression that we derived. I will just put it also down in the expression form that we just did, in the equation form, in just a moment. So we will just see what it means. Probability of occupancy of a state at energy level E1, that is the information we are looking for, that is the Fermi-Dirac distribution expression. Okay, so this is what we are looking for. What we have recognized is that given a bunch of energy levels and a number of states that exist at these energy levels, there are various distributions which can be used to distribute the electrons across all of those energy levels. We say that there is we can pick them, each of those distributions, one by one. Okay, so at a given instant we have picked a particular distribution n bar. Out of all the possible ways in which we can do this, we have picked one particular way in which we can do it. We see what is the probability that it is that distribution. Okay, so that is the first piece of information we need to know. What is the probability that it is the distribution we have chosen? Given that there are so many possible distributions, what is the probability that it is that particular distribution that we have currently chosen to look at? If you know that probability, then within that distribution, what is the probability of occupancy of a state at that energy level E1 when the distribution is that n bar? Okay. So this is therefore these two together then becomes the probability that it is occupied, that energy level at EI is occupied, given that the distribution is n bar times the probability that the distribution is n bar. If you sum it up over all possible distributions, right, so this is what this can change and this can change. So for all possible values of n bar, you calculate also what is the probability of occupancy of that state at energy level E1, given that it is that particular n bar. You sum it up over all possible distributions that you can possibly have, then you get the overall probability of occupancy of a state at energy level E1. So this is the overall piece of information that we have been looking for. So we will put it down in the equation form that we did. So this is all it is. This is this probability that I am mentioning. This is the probability that a particular distribution actually exists, that we have actually arrived at that distribution. So that is the probability. In this distribution, what is the probability that the state is occupied? So you combine the two of them and sum them over all distributions, you get the general probability that that a state at energy level Ei is occupied. So we will mark this as Ei so that it is clear that it is for a particular energy level. So this term here is also referred to in the last class I mentioned. This is also referred to as the conditional probability that state at energy level Ei is occupied. And when we say conditional, the condition that we are imposing is that at that instant the overall distribution is also n bar. Here that condition is not there. There is no condition on what the distribution is because we have summed over all distributions. Since we are summing over all distributions, there is no further condition placed here. Whereas here within this bracket there is a condition that it is a particular distribution and we are multiplying by the probability that it is that distribution. Okay, so there are two probabilities being multiplied here, a probability that a particular distribution is arrived, and within that the probability that in that distribution what is the level probability that a particular energy level is occupied. So we also wrote this in a by recognizing what the terms represent, we wrote it like this. Okay. So this P of n bar, which is the probability that we have arrived at a particular distribution or the probability that we do have that distribution, is simply the number of ways in which you can arrive at the distribution divided by the total number of ways in which you can arrive at all possible distributions. Okay, so that is by definition of what a probability is, that is what it is. The number of ways in which you can do something by the total number of ways in which you can do everything is the probability that you can do that something, right. So this is the number of ways in which you can arrive at a particular distribution divided by the total number of ways in which you can arrive at all possible distributions. So this is the denominator is actually a sum across all the possible all such terms over all other distributions. So we arrived at this term. Then I also indicated the fact that we are using the approximation that is typically used for such statistical distributions, which is the statistical mechanics approximation, which basically says that there is one particular distribution n bar, let us say n bar naught, so that some particular distribution n bar naught. Okay, so there exists an n bar naught which results in the maximum possible value for the corresponding okay. So we are assuming that there exists an n bar naught, okay, which results in the maximum possible value for the corresponding w or omega n bar naught, if you capital omega n bar naught or capital W n bar naught if you want to call it, which is where we are essentially saying that there is a particular distribution where if you actually figure out the number of ways in which that distribution can be arrived at, okay. So if you just look at the number of ways in which you can arrive at the distribution, that value will be a huge number relative to even the very next number that you can arrive for the very next distribution. So in other words, you take all possible distributions, you arrange them in decreasing order of occurrence, okay. So the maximum, so this is the maximum occurring distribution, so this is on top W n bar naught. So let us say the next most occurring distribution is n bar 1. So you will have just for example, let us say this is W n bar naught, and let us say the next so this occurs the maximum number of times, W n bar 1, W n bar 2 and so on, where n bar 1, n bar 2, n bar 0, n bar 1, n bar 2, n bar 3 and so on are different possible distributions. okay. So for each distribution we have done the math and figured out how many ways you can arrive at that distribution. So we find that and we arrange that in decreasing order. So therefore the maximum one is sitting right on top, which is W n bar naught, and what we are we find that so there exists a certain n bar naught which results in the maximum possible value for the corresponding W n bar naught. Statistical mechanics operates on the principle that this number is much larger than W n bar 1, it is much larger than W n bar 2, it is much larger than all the terms below it, because after all they are in decreasing order. So if it is significantly larger than W n bar 1, it is therefore significantly larger than all the other terms also, but more than that it is significantly larger than the sum of all the other terms. It is not just significantly larger than the next term, it is significantly larger than all of these terms together, taken together. So therefore when you calculate W total, okay, which is the term here in the denominator here, W total, okay. So W total is in the denominator, that is the sum of the W n bar 0, W n bar 1, W n bar 2, W n bar 3, like that you sum all of them. If you sum all of them you arrive at W total, but I am also saying we are recognizing the fact that in all those distributions that are available to you and the number of ways in which all of them can be calculated, we are finding that W n bar 0 is significantly larger than all the other terms and it is significantly larger than the sum of all the other terms. Therefore when you take W bar total, since it is all of these terms together and we find all of these are smaller than this, it is in fact almost equal to W n bar 0. So that is a very important approximation we are making, an approximation that which basically says that the W n bar 0 is so large, and we did this in a very specific example of 2 particles, 3 particles and 4 particles. We found that progressively the most probable distribution is occurring more and more, is becoming more and more probable than all the other distributions combined, or at least certainly the second most probable and so on. So if you look at it, when you go to large systems, not just 2 or 4 particles, when you go to 10 power 23 particles, this approximation begins to look very good, where you have the most probable distribution or the distribution that occurs the most number of times being more or less equal to the entire total of all the distributions together, okay. So therefore what we will say is that our entire calculation and our approach is based on this idea, which is reasonable for the system that we are dealing with, okay. So it is not just an idea arbitrarily thrown in, it is a reasonable idea for the system we are dealing with. So we are saying that there exists an n bar 0 which results in the maximum possible value for the corresponding W n bar 0 and which creates this situation that the W total is almost equal to W n bar 0, because it is not just a marginal maximum, it is a maximum by a long stretch, it is much larger than everything else combined. So therefore if you go back to our original expression, if this is W n bar 0, then this term by this term is essentially equal to 1 more or less, because they are both more or less the same, okay. So therefore if you are able to identify this maximum distribution, we have the following situation. Therefore okay. So we find that while we originally had, if you go back to our original thing, we had several terms in this equation, because we do not know how many distributions we have a huge number of distributions possible, and therefore this had several terms here, but we found that when we reach a maximum which is this n, it is not just any arbitrary n bar, but it is n bar subscript 0. When you do that, the term here is almost equal to the term at the denominator, so therefore this reduces to 1 or can be approximated to 1. Therefore now the contribution of this term to this FEI is almost entirely 100%, okay. So therefore we find that our probability of occupancy of a state at energy level EI, which is the general probability of occupancy of that state at energy level EI, is the conditional probability that that state at energy level EI is occupied, subject to the condition that we have reached the distribution that is the maximum possible distribution in that system, or the most probable distribution in the system, right. So therefore we reach this, and with this approximation we realize that it is enough if we focus on this term. In fact more than this and therefore this is what we are really interested in. So in fact all we are looking for is Ni by Si at 0. Si is anyway fixed, so Ni 0 by Si, in fact we can just call it Ni by Si, Ni 0 by Si 0, where Ni is the number of particles, where Ni 0 is the number of particles at energy level Ei under the condition that the distribution is n bar 0, and therefore when you get Ni 0 by Si, which is the number of states at energy level Ei, you have already got this term here, and it also turns out to be this term here. Okay, so therefore all the mathematical approach that we are doing is simply to get us this term, and once we reach here we have got the answer that we are looking for, fine. So this is what we will do. So we also so we now said that we are now interested in looking for the distribution n bar 0 which maximizes W n bar. Okay, so to do that we start out with the number of ways to distribute Ni particles in Si states. Okay. So for a given distribution we say that there is Ni particles sitting in Si states. How many ways can you make, how many ways you can do this arrangement? It is simply Si factorial Si factorial by Ni factorial minus in times Si minus Ni factorial. So this is the same as saying you have Ni particles and which are of the same kind, and you have Si minus Ni empty spaces which are of the same kind, so empty states. So how many ways you can arrange them? This is the number of ways in you can arrange them mathematically, right. So therefore if you look at the number of ways in which you can attain a particular distribution n bar, it is the number of ways in which you can arrange the number of ways in which you can create I mean distribute n0 particles in S0 states at energy level E0 times the number of ways in which you can distribute n1 particles in S1 states at energy level E1 times n2 particles in energy level E2 in S2 states, and so on. Each of these terms will look like this: Si by Si factorial by Ni factorial times Si minus. So just write it down, we will put it as S0 factorial by n0 factorial times S0 minus n0 factorial times S1 factorial by n1 factorial times S1 minus n1 factorial. So you have such terms. Okay, so this is what, this is the total number of ways in which you can arrive at a particular distribution n bar. Okay, because in each of those states you can do all of these arrangements, and the states, the minute you say n bar, that means also you have fixed the values of n0, n1, n2, n3, n4 and so on. Already as I mentioned, for this kind of system we are dealing with the Ei, in other words E0, E1, E2, E3 etc. are already fixed for the system. Si are also fixed, which is the number of states at each of those energy levels. So S0, S1, S2, S3 etc. are already fixed. Only the number of particles that are possible in each of these states is a variable through the entire problem. But when you fix a particular n bar, even that becomes fixed. For that particular distribution, the values of n0, n1, n2, n3 and so on are also fixed. Once all of these three are fixed, you can make a calculation for these terms. Okay, so like this you can make the calculation, therefore you come up with this. So therefore actually if you want to write it in a simplified notation, we simply write Wn bar is pi over I, which in just the way you would use sigma for sum, we use pi for a product, Si factorial by Ni factorial times Si minus Ni factorial. So this is the term we have. Now our purpose is given that this we have this expression, we would like to understand what can we do to maximize this expression, okay, because that is all our problem is. Once we maximize the expression, we have got n bar 0, okay. So our intention is to get n bar 0, and so therefore we just have to find a way to maximize this expression, and it turns out that the form of Wn bar is such that if you maximize Wn bar, it is the same as maximizing ln Wn bar. Both those functions behave in essentially the same way, they all monotonically increase, so to speak. So therefore Wn bar, if you can maximize, it is the same as maximizing ln Wn bar. So and mathematically it is easier to handle ln Wn bar, so therefore we just look at ln Wn bar. So therefore we write ln Wn bar, we write the expression for it, and that is simply what is a product will now become a sum, sigma over I ln Si factorial minus ln Ni factorial minus ln Si minus Ni is factorial. Okay, so this is the if you take the natural logarithm of Wn bar, then this is what you will get, right. So we also recognize Stirling's approximation, and Stirling's approximation for a factorial is simply that ln x factorial is x ln x minus x. We did the same kind of approach for Maxwell-Boltzmann statistics as we are doing for Fermi-Dirac statistics. Mathematically similar steps were involved, so you can always look at our derivation for the other distribution and see how they compare, and we will find therefore that we can write ln Wn bar equals sigma over I Si ln Si minus Si minus Ni ln Ni minus Ni plus Si minus Ni ln Si minus Ni minus Si minus Ni. Okay, so this is what we will get. Now if you look at this, you have a minus Si term here, there is a minus here and a minus here, so therefore this becomes a plus Si, right. So therefore this will cancel out with this term here. You have a minus Ni here, there is a minus sign here, minus minus will become plus, so minus Ni and a plus Ni, so these two will cancel out. So therefore this is simply sum over I Si ln Si minus, we will remove this bracket, minus Ni ln Ni minus Si minus Ni ln Si minus Ni. So this is what we have. Now I also want you to understand that in our system, in the derivation, the stage that we are in this derivation, at this moment Si is also Si is already fixed for the system as is Ei, so that we have no choice over, but we are in the process of maximizing finding the condition for maximizing n bar. So in that process what are we doing? We are actually trying out different possible combinations. We are trying out, we are taking some n particles we have at a given energy level, we take a few particles from there, we move it to some other energy level, then we again calculate this capital Wn bar. We want to see whether we have gone up in quantity or gone down in quantity. So the Ni values, the values for Ni that we have here are actually not yet constant. We are playing around with that value to figure out what is the maximum that you can reach for this term here, right. So therefore this is a variable that we have in our system, Ni. Si is not a variable, it is a constant. Now assuming you do reach a maximum, okay, so when you reach a maximum, the one of the ways in which we describe a maximum is that if you have reached a maximum, marginal changes in the quantity will still keep you at the same value. So in other words, d ln w n bar by del d n ni will reach a 0, okay, d ln so when this function reaches a maximum with this variable, d ln w n bar by d n I should reach 0, or in other words the other way of writing it is we write del ln w n bar equals 0 implies sum over I. Now we have to do differential of these terms with respect to ni. The first is a constant, so the differential of this term with respect to ni is 0, okay, so if you want for clarity's sake we will just write 0 here for the first term. The second term, there are two places where ni arrive, so therefore we will write minus del ni ln ni and then minus ni into 1 by ni del ni, okay, so differential of the first term times the second term, and the differential of the second term which is here times the first term which is here. Similarly minus you will have minus del ni ln Si minus ni and minus Si minus ni into 1 by Si minus ni, okay, times minus del ni. Okay, so same thing I have done. So this first term comes to 0, this becomes two terms because you can differentiate the first term leaving the second one constant, or differentiate the second term and leave the first one constant, so these two terms arrive. Same thing you can do with the last term. So minus sign is still here, so minus del ni ln ni ln Si minus ni and minus Si minus ni by 1 by Si minus ni minus del ni. So this is the terms that these are the terms that we have. So we will just simplify it here. So this is equal to, so this is equal to 0, okay, so this is also equal to 0, so both of them are, they are all equal to 0. So if you write this just simply mathematically simplify this, we will have minus del ni, so this is sum here, sum over I minus del ni ln ni, okay, this is going to be simply minus del ni. This term here will also remain, so this is plus, minus and minus will become plus, minus del ni sorry plus del ni ln Si minus ni, these two will cancel, minus and minus will cancel, so you will have plus del ni and this is equal to 0. Okay, equal to 0. So this is what we have. So therefore these minus signs will, this minus del ni and plus del ni will cancel. Okay, so therefore we now have a simple So if you look at what we have just put down, this is what we have got, del ln w n bar is simply the sum over I of minus del ni ln ni plus del ni ln Si minus ni. Okay, so this is the and this is equal to 0 because we have reached a maximum, or we are looking for the condition of maximum, and when the maximum is reached this is going to be a 0. Or to simplify even further, we will simply write it as sum over I del ni of ln Si minus ni by Ni. Since this is a minus ln Ni, the Ni can go to the denominator, so therefore we will end up with this. So under the condition of maximum, this sum is equal to 0. So we have one equation here, equation 1. I also said that the number of particles is conserved. Therefore, the sum of all the particles equals a constant, right. So sum of all the particles available in the system is a constant. Therefore, any changes in this number of particles should be the total sum of all changes that you can make in these particles. You add some particles at one location, you remove some particles in another location, that total the sum of all the changes that you make has to work out to 0, right, because you removed 5 particles means those 5 particles have to go somewhere. So if you put minus 5 particles at some place, you have to put a plus 2 and plus 3 somewhere else, so that the sum works out to 0, otherwise you are removing particles from the system. So therefore that has to work out to 0, therefore sigma over I del Ni equals 0. And you can see also equation wise, if the sum is a 0, I mean it is a constant, if you differentiate it, it is going to be 0. Similarly, the energy in the system is conserved. Therefore, sigma over I Ei Ni equals 0. The energy states are anyway fixed, so Ei is already a constant, you do not have a choice in it, only Ni can change. So once again, if the energy is conserved, if you even shift particles between the various energy levels, the total change in energy that you are creating, if you are creating adding some energy at one location, you have to remove exactly the same amount of energy from a bunch of other locations, could be one or more other locations, okay. So that process of adding energy to one location versus removing energy from the other location should match up so that they reach a 0. So therefore, since I am sorry, this is not 0, this is a constant, this is not 0, this is a constant, just the way this is a constant here. So therefore the changes in it has to be 0, okay. So the change, the sum of the changes has to be 0, the actual sum has to be a constant, it will not, it does not have to be 0, it has to just be a constant. So this is what we have. So if we can call this conservation of number of particles as equation 2 and conservation of energy as equation 3. So we have 3 equations here. The first one is the process by which we try to the equation that we arrived at by trying to maximize the number of arrangements that you can have in a particular the number of ways in which you can arrive at a particular arrangement n bar. In that process we arrived at one equation. The conservation of number of particles in the system gives us equation 2 and the conservation of energy in the system gives us equation 3, all of which equate to 0, right. Now having got this these 3 equations, we will use the method that we did when we also tried to derive the Maxwell-Boltzmann statistics, which is the Lagrange method of undetermined multipliers. So we have to use the Lagrange method of undetermined multipliers. Okay. The point is we are trying to maximize a particular quantity, in this case ln omega bar ln n bar, ln of w n bar, we are trying to maximize this subject to these 2 constraints. That is the basic problem that we have. To put it in words, we have to maximize this expression or ln w n bar, which means we work out to, which implies that we have this expression should work out to be correct, right. The process of maximizing this implies this equation has to hold true, but it does not have to arbitrarily hold true, or it cannot arbitrarily hold true, it has to hold true subject to these 2 constraints, 2 additional constraints we have placed on the system, which are 2 other equations which are valid for the system. And I mentioned the last time we discussed the Lagrange method of undetermined multipliers, that the basic idea is it is like saying that you are trying to walk along a hill and trying to find the maximum point on that hill, okay. So you have lot of an uneven surface going up and down and so on, you wish to find the maximum point on the hill, but our problem is not simply to find the maximum point on the hill. If it were only to find the maximum point on the hill, only the first equation would hold, that is, in other words, it is necessary only to solve the first equation. But additionally we are saying it is not just to find the maximum point on the hill, but you are subject to the constraint that you have to walk along a path. Okay, so you are walking along a particular path, and that is the kind of constraint we are creating by putting in additional equations. By putting in additional equations, we are saying you have to stay along a particular path, which could be some arbitrary path we are saying. So some arbitrary path you are moving along. In that path, what is the maximum that you are reaching in that hill? Clearly that need not be the highest point in that hill, right. So you may walk across in such a way that half the height of the hill is the highest point that you are reaching along that path, along that hiking trail, so to speak. So the maximum point that you reach when you travel along a particular path need not be the absolute maximum point of that hill. It is some point subject to this, some maximum subject to these constraints. So when you do, so that is the kind of problem that the Lagrange method of undetermined multipliers tries to solve. It simply says that for you to be able to solve these like this, we will assume upfront that there is a certain constant that with which you can multiply this equation and another constant by which you can multiply this equation, and such that you can add all of them together, and that would equate to 0. It is the same as saying that you are now trying to separate out the variables, separate out the del ni. So in other words, what we are saying is that we are basically saying we are going to do equation 1, and we just for convention's sake we are just going to take the negative of that equation because it works out conveniently for calculations, plus equation alpha times equation 2 plus beta times equation 3 and equate to 0. Anyway they all equate to 0, so therefore you can always do this, but we assume that there is an alpha and beta which enable us to separate the various ni, del ni. Okay, so therefore we are going to say this implies sum over I of okay. Equation 3 had Ei del ni sum of Ei del ni equals 0. I have simply pulled Ei in and kept del ni out, multiplied it by beta, so that beta shows up here. Equation 2 simply said sum of del ni equals 0. So I have multiplied that by alpha, and I have just pulled the del ni out of the bracket because it is a common term. So you just get C alpha here. So it should have actually just been alpha del ni. Equation 1 is the same what we already had, which was that the sum of ln Si by minus Ni by Ni equals 0 times del Ni equals 0. I again pulled del Ni out, and I have put in a minus sign here. So just for convention's sake, because the answer then works out in a manner in which you can explain it better. But there is no harm anyway. We have not done anything inherently wrong, because anyway the sum is equal to 0. So whether the sum is equal to 0 or you put a minus sign by in front of it makes no difference. It still is 0. So there is no nothing particularly wrong that we have done, right. So and all we are saying is that we assume that there exists an alpha and beta, and we don't know upfront that they do exist. We assume that they exist such that if you write this equation up, the variables, each of the ni is now a separate variable. We are able to separate the variables out. You can perhaps look up a mathematical book for the Lagrange method of undetermined multipliers and see if you can understand the manner in which this is done. What I am explaining to you is the method in which it is done and the reasoning used behind it, but there are several books which will explain it, so you can look that to see if in case you are not understanding it for any particular reason, you can look up a reference, a mathematics, engineering mathematics book or any other mathematics book to specifically look at this Lagrange method of undetermined multipliers. So if you do this, we are saying that for this to be generally true, regardless of the value of del ni, right, for this to be true regardless of the value of del ni, because you have wide variations of del ni available, right. So when you are saying that you are reaching a maximum, you can change del ni, you can put in more particles in one location, less particles in another location. The variety that you have on del ni is quite large. You can always do this indefinitely, but you are saying that this sum should always equate to 0, right. We are saying that individually we understand why these terms should equate to 0, why this time del ni should equal 0, why this term should equal 0, and why this last term should equal 0, equate to 0. So this we understand individually. We also understand that this sum, because simply because we have multiplied by some constant and each of these terms is in the sum equals 0, we understand that therefore this whole equation should also equate to 0. So there is no controversy there. Where we are now taking a step forward is saying that the del ni are values that you can change in a significant manner through the system. You have no real control on del ni, or you would like that to be free. You would like to be able to change the del ni independently. You should be able to add more here, less there, and so on. You have no real control on del ni, except to say that the overall sum has to be 0, but you can do more or less and so on. Therefore, to always ensure that this sum always equals 0 regardless of values of del ni that you have or you are employing in the system, what you are actually requiring is that the first term should equal to 0, should equate to 0. The only way you can guarantee that this entire sum equals 0 regardless of values of del ni that you are selecting is to guarantee that this term is individually equal to 0. If this term is if this term always equates to 0, then it does not matter what you are doing with this term, you will always get 0, right. So if this term equates to 0, does not matter what these terms are, and it does not matter that you are taking a sum over all I, you will always get 0 because this term is guaranteeing that it is 0. Therefore, the only way to guarantee that this is 0 is to ensure that the first term equates to 0. So that is the important step that we are additionally taking. Therefore, we are saying that this implies that minus ln Si minus Ni by Ni plus alpha plus beta Ei equals 0. So we will just simplify this marginally, we will just move this term to the other side. So therefore, we are saying ln of Si by Ni minus 1 equals alpha plus beta Ei. Okay. Now please recognize the fact that this is the equation we are arriving at when we have reached the maximum the distribution that occurs the maximum number of times. In other words, when by the time we have arrived here, we are not talking of any arbitrary distribution, we are talking of the maximum distribution. Okay. So so in fact the Ni is not some arbitrary Ni, it is Ni 0, so to speak, okay, corresponding to n bar 0. So that is where we have arrived at in the process of all this mathematics, but we will we will get to that in just a moment. In this equation, therefore we are saying that Si by Ni minus 1 equals e power alpha plus beta epsilon I, beta Ei. Okay. So therefore this implies Si by Ni equals 1 plus e power alpha plus beta, right. I am just rearranging the terms here, this log becomes since I have removed the log, this goes to the exponent. So that is why we have e power alpha plus beta Ei and Si minus Ni, I have just used Si minus Ni minus Si by Ni minus 1, minus 1 goes to the other side, so it is 1 plus e power alpha plus beta Ei. Now note a couple of things, we have arrived at Si minus Ni. I started off by saying we need Ni by Si, so we need the inverse of this, right. So that is all we are really looking at, so we will just put down the expression for that. So I will just put it down again, Si by Ni equals 1 plus e power alpha plus beta Ei. Therefore Ni by Si when n bar 0 has been attained. Okay. So when n bar 0 has been attained, so Ni by Si we can in fact designate now by Ni 0, subscript 0, indicating that we have reached the maximum possible distribution. It is not some arbitrary distribution, it is simply 1 over 1 plus e power alpha plus beta Ei. Okay. So these EI are energy levels that are there in the system, and there are several different energy levels. For any given energy level, the number of the probability of occupancy. So this is f of EI. I told you upfront that f of EI is the general probability of occupancy of a state at energy level EI, but it is also equal to the probability of occupancy of the state at energy level EI, subject to the fact that we are only working with the distribution that is the most probable distribution, and that is what this n bar is, n bar 0 is, and we have attained this mathematical expression we have reached in accordance with all of those constraints that we have placed. This alpha and beta, alpha works out to EF, some constant EF by kBt minus EF by kBt, and beta works out to 1 by kBt, where T is temperature and kB is Boltzmann's constant. This is EF here is a constant, so alpha is also a constant, EF is also a constant. What it represents we will see a little later. So the f of E, so I'll just write here f of E I or E, f of E, in the general case I would be some particular energy level, which is what we are designated by this energy value E. F of E is simply Ni naught by Si naught. If you want, we can write EI and we will specify it, specify that thing little later, generalize it little later. So we have simply 1 by 1 plus E power EI minus EF divided by kBt. Okay. So this is the probability of occupancy of a state at energy level EI, and this is given by this expression 1 divided by 1 plus E power EI is that energy level EI that we are talking about, minus some constant EF which we have not yet described in any great detail. It is some constant, the whole thing both E minus EF are divided by kBt, which is the Boltzmann's constant times the temperature T. Okay, so this expression here is the Fermi-Dirac expression. Okay. So this expression that we have arrived at here is the Fermi-Dirac distribution expression for the Fermi-Dirac distribution, and to summarize, this is an expression that holds for a bunch of fermions which are particles that are identical and indistinguishable, and they follow Pauli's exclusion principle, which usually means, and a fermion also therefore essentially means that it has to have a half integer spin. So electrons in a solid qualify as fermions, electrons qualify as fermions, and the system we are dealing with is a whole bunch of electrons that are existing within a solid, which happen to be moving freely through that solid. So the Fermi-Dirac distribution that we have derived will apply perfectly fine or perfectly well for the system that we have chosen, and this is the expression that we have arrived at for this system. So what we will do in our next class is we started this by saying that we have a Drude model which we have now modified to the Drude-Sommerfeld model. The Drude-Sommerfeld model is treating the electrons as quantum mechanical particles which are following Pauli's exclusion principle, and therefore Sommerfeld essentially took Fermi-Dirac statistics and employed it and ensured that it and applied it to the distribution of electrons in the system, and therefore to the Drude model. And to understand that process, we have now derived the Fermi-Dirac distribution. So what we will do in the next class is we will look at we have now come up with an expression, mathematical expression for the Fermi-Dirac distribution. We will make a plot of this this distribution, and we will compare it with the Maxwell-Boltzmann distribution, and then therefore we will see that by assuming that this is the distribution that holds within the system, what is the actual fundamental difference we have made with respect to the model that exists for the electrons in the system. Since we are now saying that the new model does Sommerfeld's modification of the Drude model, and hence the Drude-Sommerfeld model is employing this distribution, what is the implication of it is something that we have not yet considered. we have just mathematically arrived at that particular distribution. When once we put it down in the form of a plot, we will get a better understanding for what is the implication of assuming that this distribution holds for the electrons in the system. What is the implication of this distribution in terms of the predictions that we can make of the properties of the electrons, and therefore the properties of the entire solid, which are largely determined by those free electrons in metallic systems. So we will do all of that in the next class, and we will halt with this distribution today. Okay, thank you.